Today, it's been a long day with a lot of topics, but I do think this is a great kind of cap off to today's discussion for a number of reasons. The first, as Patrick mentioned, today is the Agency Innovation Mission Day. So as the agency is thinking about how we can be more innovative in the things we do, it's good to spend some time here. But I also think it's a good kind of capstone to a lot of the conversations that we've had today. We've seen, just what Jim talked about, some new paradigm thinking. And if you use kind of at the simplest term, innovation being new ideas, devices, methods, I think it's important. And the other word that I think was important today is balance. So we heard a lot today about the need to really reflect and be grounded in the lessons of the past, both our successes and our failures. But I think we've got to balance that with new approaches and staying relevant and current in the changing times. And this morning, Greg, you mentioned how it's generational changes since we did this the first time, and not only in people, but I think of what the technology was the first time through, and what the technology will be 10 years from now, we can't even imagine. So being able to be relevant and change and a learning and adapting organization, I think is important. So I think it's a good that we focus on that today as well. Let me introduce my fellow panel members, and as Patrick said, there is a lot of experience, probably over 100 years here, so really pleased to be able to, and it's all coming from Pat, and it's really my pleasure to introduce and to moderate this panel. So first, on my left is Chris Moore. Chris is currently the Deputy Director of Advanced Exploration Systems Division within the Human Exploration Operations Mission Directorate at NASA headquarters, where he leads the development and testing of prototype systems for future exploration missions. Chris has over 30 years experience at NASA and has managed 5 major technical programs since 2002. And prior to that, he worked at NASA's Langley Research Center. And then we also have Bob Bagdigian. And Bob comes from the Marshall Spaceflight Center. He's actually currently assigned to the Office of the Chief Engineer, where he's serving as the Deputy Chief Engineer for HEO. Bob also has over 30 years experience, and primarily in the development of environmental control and life support systems. And that has taken him through ISS, through different technology demonstration tests, and in project management and in branch chief management roles. And then we also have Pat Simpkins. Pat is the Director of Engineering at the Kennedy Space Center, where he leads the strategic direction and leadership of large multidiscipline engineering organization in a matrix environment. His organization supports many of the agency's missions, including GSDO, Commercial Crew Program, ISS, and Technology. Pat also has over 30 years experience with various roles, and including the Director of Human Resources, so brings, again, some different thinking. And as each of the gentlemen here go through their presentation, they will maybe share a little bit more with you on what brought them here into this topic today. So for today, what I'm going to do is we'll turn it over to Chris. Chris is going to talk about innovation within advanced exploration systems, kind of give an overview thinking of innovation at NASA, and talk a little bit about cultural innovation. Then Bob is going to talk kind of on the hardware side and balancing, again, our key word of legacy versus innovation in hardware systems. And then Pat will touch on kind of a process innovation. And I think that'll give us a good round out of the different ways to think about how we can continue to improve and to learn. And then we'll have questions and answers at the end. And so with that, I'll turn it over to Chris.
Good afternoon, everyone. Up to this point, we've heard a lot about avoiding risk. I'm going to talk about taking risk and how that drives innovation. So you heard this morning that the journey to Mars is really hard, and it's going to require a lot of technical innovation. And Advanced Exploration Systems program is developing prototype systems that incorporate new technologies and testing those in ground and flight experiments. And by its very nature, technology development is innovative because we're doing something completely new. So I'd like to describe the different types of innovation. The next is business model innovation, and that's looking at new ways to involve commercial partners through public-private partnerships, and also engaging the public through crowdsourcing and price competitions. And then finally, there's cultural innovations. It's trying to create a new culture within the agency that awards innovation by taking risk, learning from failures, providing hands-on experience for the NASA workforce, and streamlining management practices so that people are free to explore new ideas. So I'd like to show you this example of a public-private partnership, which was development of the Bigelow expandable activity module, which was deployed on the ISS in May. And this approach involved a fixed price contract with Bigelow Aerospace, so that this allowed the government and Bigelow Aerospace to share a high level of risk. NASA is developing technology for a deep space habitat, where Bigelow Aerospace could take that same technology and use it to develop a commercial habitat in low Earth orbit. We supported the partnership by providing the berthing mechanism that docked the module to the ISS through a contract with Sierra Nevada Corporation. We helped with payload integration on the SpaceX cargo vehicle, assisted with the ISS flight certification and safety review processes. And we provided engineering expertise to help Bigelow Aerospace resolve technical issues with predicting and controlling the module's deployment dynamics. But this was a very successful approach involving a fixed price contract. The next public-private partnership I'd like to highlight is our next step, Habitation Systems. We're trying to deploy a habitat in the proving ground of cislunar space in the next decade, so that we can evolve capabilities over time to increase mission duration up to the point where we can accomplish a one-year shakedown cruise. And we had a lot of direction from Congress in this area. They said we should develop a prototype cislunar habitat by 2018. So to move out quickly, we issued a broad agency announcement, and we selected 4 phase 1 partners to do a one-year concept studies on these various habitat configurations. That was Bigelow Aerospace, Orbital Sciences, Lockheed Martin, and Boeing were the initial phase 1 providers. And the unique feature of these partnerships is that industry has to contribute some of their own funding. In the phase 1 activities, they contribute 50% of the cost. This could be labor cost, it could be test facilities, it could be independent research and development, and other in-kind contributions. We wanted to provide an on-ramp for additional providers for phase 2 development, which moves from conceptual studies into hardware development. So we had a second round of the solicitation earlier this year, and we selected 2 new providers, NanoRacks and Sierra Nevada. So we have 6 companies. 5 of them are building prototype habitats for ground testing. NanoRacks is a study to look at how to outfit an upper stage propellant tank so that it becomes a habitat. The plan is to have these prototype habitats delivered to NASA centers, and we would test out subsystems like life support and power and avionics. We'd evaluate human factors, and we'd verify interfaces. In parallel to hardware development, we're developing standards for interfaces and the design of systems. And at the end of phase 2, which culminates in 2018, we'll be ready to move into procurement of the flight system. But we're going to take the best features from all 6 of these companies and combine them into a government reference architecture for the habitation system. The next type of partnership is a little different. This is called Lunar Catalyst, and its objective is to stimulate a commercial lunar payload delivery service for small payloads. And we're working with 3 small companies, Moon Express, Astrobotic, and Madison Space Systems, to develop these capabilities. We're working with the partners through an unfunded Space Act agreement, which means we do not provide any cash to these companies, but we do support them with engineering expertise, analysis, test facilities, and loaned hardware and software support. And this helps them accelerate their development efforts. A number of these companies want to fly their first missions in the 2018 timeframe, and Moon Express and Astrobotic are also competing for the Google Lunar X Prize, which gives them additional incentive. At the end of this Lunar Catalyst activity, once these companies have demonstrated the ability to land payloads on the moon, we intend to procure payload delivery services for small instruments and technology demonstrations. But we're not going to be the anchor tenant. We're not going to be the sole customer. The companies have to raise their own financing and attract other customers. So we'll just be one of many customers on these landers. So those are some examples of public-private partnerships. We're also engaging the public through the NASA Tournament Lab. When NASA has a challenge and they want to look at alternate solutions, we post these challenges on the web, and people from all over the world can submit ideas on how to solve these challenges. And we'll award the winners a couple $1,000s for their ideas. This can range from software development to hardware. And AES and NASA have been a pioneer in this approach, and we've been asked to lead for the whole federal government various activities that encourage prize competitions in other agencies. So we're working closely with other agencies to involve them in these competitions. Another area of engaging the public is through our CubeSat launch initiative. CubeSats are small spacecraft that can be built for low cost by educational institutions and nonprofit organizations. The CubeSat launch initiative provides launch opportunities on government and commercial missions. And so far we've launched about 46 of these CubeSats over the last few years. And not only do we inspire the next generation of NASA employees by giving them hands-on experience with developing flight hardware, we've also learned a lot from their experience, and we're incorporating CubeSats into our mainstream AES program to do robotic precursor missions. We plan to launch 13 CubeSats on EM1, the first launch of SLS, to look for lunar resources, study the effects of deep space radiation on simple organisms, and to fly by a near-Earth asteroid with a solar sail. So we're learning by reaching out to the public what we can do internally as well. And then finally, we had these future engineers challenges where we've requested ideas from students on parts and tools that can be printed on board the ISS using a 3D printer. And so the winners get to visit NASA Mission Control and watch their part being printed in real time. So these are some ways we're engaging the public. So let me talk now about cultural innovation. We all know the story of Apollo 13, where Gene Kranz charged his team, failure is not an option. And certainly in that case where human life was on the line, that was a very appropriate thing to say. But somehow that failure is not an option. Culture is permeated throughout the agency, and we're afraid to take risk in areas where it makes sense to do so. So it's shifting from failure is not an option to failure is acceptable as long as we learn from each failure and we improve. Another type of innovation is programmatic innovation. When the AES program was created about 6 years ago, we had a lot of people rolling off the canceled shuttle program, rolling off the canceled constellation programs. And so we had to find a new way to employ civil servants, and we gave them focused in-house technology development activities to give them experience in developing systems with their own hands and learning new skills. And we've tried to streamline the management overhead. There's no project offices. We manage the program out of headquarters. And all of our projects work across the agency. They involve multiple NASA centers. And we try to eliminate any unnecessary requirements, reports, and reviews, because we want people to spend time working and innovating instead of reporting. And we encourage our project managers to pursue new ideas and take risks by awarding innovation. We award a $10,000 prize every year to the most innovative AES project that's voted on by their peers. So I'm going to summarize these various approaches with this matrix that comes from the Harvard Business School, but it's a good way to look at the relative balance between technical innovation and business model innovation. So in the lower left quadrant is sort of the routine way we do business. We have international partnerships for the ISS, where each country or space agency contributes a critical element to the overall system. We also have the ESA development of the Orion service module. So this is an existing partnership model, and it uses existing technical competencies. The beam inflatable habitat is an example where we require new technical competencies. We've never demonstrated inflatable structures for space habitats until now, but it's using an existing business model, which is a fixed price contract. In the upper left corner as an examples of disruptive innovation, where we have both new business models and we require new technical competencies. The commercial crew program is involving the industry providers in development of the human safety rating requirements. The Lunar Catalyst activity involves new business models to Space Act agreements, and where no cash is transferred to the contractor, but it's using existing technical competencies. We already know how to land on the moon. We're just trying to encourage the commercial industry to develop their own capabilities. And the same with the NASA Tournament Lab. It's usual challenges, but it's a new way of engaging the public through these widely competed prize competitions. The next step, Habitation Systems, involve both technical innovation and business model innovation, as do the CubeSats and in-space manufacturing. So in the long term, we want to move from the lower left quadrant up to the upper right quadrant, where we have both new business models and new technologies, and this will allow us architectural changes in the way we do exploration, doing exploration in a totally new way by engaging the public and the private sectors. And we're entering a new era of collaboration within NASA. So, thank you.
I'm going to talk about the challenges of trying to find that right balance that Tom was talking about earlier, the right balance between heritage and innovation. And I'm going to use environmental control life support as the example through That's where I spent predominant part of my career. You've all seen this, the Squid Chart, where we're now operating routinely in low Earth orbit and progressing out through proving ground ultimately to achieve the point where we're truly Earth independent and being able to explore Mars and Mars vicinity. So from the NASA life support perspective, we've been spending a large amount of time and attention looking critically at where we are capability-wise today, operating in low Earth orbit in an Earth-reliant fashion, and I'll describe it a little bit, and asking ourselves how much of what we have today can be directly usable in the next steps, how much of it do we need to improve, and what are we missing that we don't have today. So that's a little bit what I'm going to talk about. Next. The nice thing about space station, obviously it's a very challenging environment, but the nice thing is you got Earth right there. Obviously, in this view, it's obvious. Relative to solar system dimensions, it's really close nearby, and we can actually do take advantage of that in how we operate our life support systems. On space station today, we've accumulated since the initial manning of the station over 5,800 days of crew operations on the station. During that time, we've been day in, day out, we've been moving air, we've been controlling temperature, controlling humidity, we've been scrubbing carbon dioxide out of the atmosphere, we've been scrubbing trace contaminants out of the atmosphere, keeping the crew comfortable and functional and able to do what they're supposed to be doing up there, which is doing science. For the last nearly 3,000 of those days, we've actually been recovering water from crew-generated wastewater and generating oxygen. The latest statistics I have is we've recovered about 28 metric tons of water. That water is available, and again, that's water that's being recovered predominantly from what the crew is putting out, urine and sweat and respiration water. That water is being turned right around, and the crew can use that for drinking and food prep, some basic hygiene functions. And a portion of that water has also been used to generate about 5 metric tons of oxygen for the crew to breathe. So you'll hear us in the life support community often refer to us operating in closed loop fashion, and admittedly a little bit of a misnomer. Despite those statistics, we're still not fully closed, and I'll talk about that in a little bit. Next chart. So how are we doing all that? I preface this by saying we're operating in low Earth orbit in relatively close proximity to the Earth. We are definitely reliant on that close proximity, and some of the ways that's manifested is our equipment has been packaged and engineered into relatively large orbital replacement units, or ORUs. That was all intentional. Again, space station is first and foremost a science lab. We didn't want the crew members to have to be spending time digging in to the innards of any of our systems and doing detailed repair work. So everything was packaged in relatively large combinations of equipment into these ORUs. So when something breaks, and when something breaks, it's usually something small. It's usually a sensor or a bearing or something like that. What we do to save crew time is we replace an entire ORU, which can be 100 to 300 pounds. So it's a relatively weight and volume inefficient approach to things. But again, what we're trying to do is limit how much time the crew actually has to spend fixing something that's broke. We also make fair use of expendable filters. Filters can, as long as you know what the makeup is of what fluid is coming to, the fluid that's coming to you, you can design filters to pretty reliably remove those constituents, but they don't last forever, just like the filter on your kitchen sink. You periodically got to remove it. And so, again, we do that on a routine basis on station. Despite those water recovery and oxygen generation statistics I just quoted you, we still, on average, since about 2011, when we completed, when we added the last bit of our oxygen loop closure equipment, since that time, we've still been needing to resupply, on average, about 0.8 of a liter of water per person per day. So if you run that math out and project that kind of performance over, say, a 1 year's worth of 3 crew in orbit, you're still up around a metric ton worth of water that needs to be resupplied. So space station technology baseline in terms of loop closure is good, but it still leaves a lot that could be done to further reduce that continued reliance on consumable resupply. And then the last thing, and this is actually a big advantage to us on station, is we are able, station's a very closed environment. Can be fairly dynamic. And so it is important for us to understand what's going on in that environment for a crew health perspective. So we do have the capability to, on a periodic basis, be able to grab some samples of atmosphere, grab some samples of water, get them manifested to come down, and then have trained chemists and well-equipped Earth-based labs do, some really detailed analyses and give us an understanding of what's going on up there. It's snapshots in time, but we can get just about any type of analysis we might feel we need. So those are some of the advantages that we have available to us on space station today. Next. So now looking out, thinking beyond first to the proving ground. Next. A lot of interest is within the agency of trying to get away from an ORU-based model where we're changing out large combinations of equipment and get to the point where we can actually start repairing stuff on orbit. We've been learning a little bit of that on space station today. However, we've been learning it on equipment that was originally designed not to be maintained on orbit. So it has been a challenge on station. We're learning from those difficulties, and I think there's a lot of benefits to be gained by repackaging some of our equipment in different ways, but always being mindful to make sure that we don't repackage it in a way that we end up with different system behavior when all is said and done. There's been some work at, the crew spends a lot of time on space station cleaning filters. In microgravity, dust doesn't settle like it does here on Earth, and so any dust or skin cells or hair or anything that's released into the cabin atmosphere sooner or later finds its way onto one of the numerous filters that are located throughout the station, and the crew has to spend quite a bit of time going around and cleaning filters, and we'd like to be able to come up with ways to reduce that kind of burden. I mentioned we were still having to recover or resupply a fair amount of water. So we are looking at ways to increase the recovery of usable water and usable oxygen from some of our waste resources that are left behind from our processes today. You might be wondering what that picture is. That's actually what is left behind when you extract about 98% of water from your urine. So don't try that at home, it stinks. And we've also been learning and have been demonstrating some capabilities to actually do some I don't want to say rudimentary, but begin taking some early steps at increasing our ability to do some onboard environmental sampling. Still a little bit crew intensive, still not quite as broad ranging as what we can do down here on the ground, but it's a good first step. Next. And then finally, ultimately, where we all want to be someday is to be Earth independent. That comes with its own set of goals and challenges. we'd like to get to the point, you hear about this a lot in recent years within space manufacturing, is being able to actually begin manufacturing equipment. So we don't need to bring individual copies of individual part numbers. We can bring the raw materials or get the raw materials locally from where we are and manufacture what we need. Once we go to Mars in particular, from a life support perspective, planetary protection becomes something that we haven't had to worry about. As the crews go in and out of their surface habitat. From a life support perspective, that a couple of unique challenges is the Martian soil is unweathered because of the lack of atmosphere there. So its characteristics, that's all, the soil particles are very small and very sharp edge, and they can wind up being a unique crew health hazard if those kind of particulates find their way deep down into the crew members' lungs. So we have to be particularly careful about making sure we don't allow any of that stuff to find its way back into habitat, which you can imagine could be a bit of a challenge, given that astronauts are going to be coming and going, and they're going to have EVA suits that they're going to have to maintain and bring inside and work on. So, but we also have to worry about the making sure that we don't contaminate the environment on space station and just about, I think, every human spacecraft to date. We've always had the luxury of venting something. On Mars, depending on where we are, we will probably likely have to have at least a much stricter control over what we vent. I don't think we'll ever get to the point where we're not venting anything, but that could wind up propagating back into our systems and changing the way we do some of our chemical processing inside of habitats. A lot of interest in recovering consumables from in situ resources, predominantly water. That's good, but there could be some environmental contaminants like perchlorates or things like that would come into our system with water from sources like that. We have to be careful for. And then finally, we really like to get to the point where we have the capability to have fully autonomous environmental monitoring and control, where the crew does not have to be operating the spacecraft, or we don't have to have a legion of ground operators making decisions about, are we going to generate oxygen today? Do we need to ramp up the fan speed? Those kinds of things. So we'd like to get to the point where we have the systems and the smarts on board for the spacecraft to be able to manage all that in the background. And that's what I got.
I did want to talk a little bit about what we've used in the past and what we're using in the future, and a couple principles that I think allow us to do this, either as leaders in organizations or engineers within the organizations or business people. Innovation, to me, is about looking around, and I'll explain that a little bit more. It's my Ferris Bueller philosophy of living. Can you go to the next slide? When I first started using this analogy, I realized half the room didn't know what I was talking about. This movie it came out in '86, so I apologize to everybody who was just a dream at the time. But Ferris Bueller had a saying that the world's moving pretty fast, and if you don't stop and look around once in a while, you might miss it. So he goes through a bunch of adventures. I'm happy to say there's actually a scene at Wrigley Field. If you go to the next slide, I wanted you to see this video, and I want you to listen.
3, 2, 1.
That was violent.
I don't know if you caught it there at the end, but the test engineer, after that all happened, said, well, that was violent. That is the first test of the first umbilical for the SLS and Orion and GSDO programs. That there were things that went wrong in there. But I got a copy of that video and sent it to my center director. I said, hey, look, you know, we did our first test. And he said, he sent me an email back, and that's awesome. Was it supposed to do that? And I replied, yes, it was a test. A couple things that you see in there, that bounce back of the umbilical plate itself probably should not have occurred. We have some innovations dialed into that, and you'll see it probably in the next picture. But I wanted to show you, just to give you an idea of scale, you can see some people down there on the ground, kind of in the background there. And this is one of our tilt-up umbilicals. We actually designed and built this umbilical for Ares 1. And the idea was that Ares 1 got off the pad so fast that the arm had to tilt up to be out of the way in time. So this test, even though that the plate bounced back, this test actually met all the requirements. It moved between 4.5 and 5 seconds. It was out of the excursion zone, and it was out of the drift zone in the 4.5 to 5 second requirement. There's a lot of other things we needed to do with this arm, but that was the first test, and it was kind of interesting. So if you go to the next slide. I wanted to show you this. On that, this is a close-up of the plate itself, and in the upper right-hand picture, you see what looks like a disc, kind of a white disc with a black rim. That's actually, that's a motor for an electric motorcycle. And what we did is we put software and hardware controls in to use that as a winch motor because it gave us the kind of response and acceleration and deceleration that we needed to pull that umbilical plate off. And we used some technology. It's state of the art. I'm sure a lot of people are using it, but it synchronizes the video and the data so that we could look at this and make sure that we didn't exceed any improper loads. By the way, this is the Orion service module umbilical. And we use this technique, this little bit of innovation here, to marry the video to the data. And the data in the lower right there is volts, it's pounds of force, it's amps, all those things you want to pay attention to because it's an entirely electric system. This arm is pulling off an ECS, several ECS ducts actually, and what we found in the videography, you could not see just watching the video, and that is that one of these lanyards bounces back. One of the wires, that one there at the bottom, bounces back into the excursion zone. So we had to go through a process of designing some fixes, and it turned out to be a very simple piece of, a metal bracket to make sure, to hold that lanyard out of the way. That upper right-hand picture, we use a honeycomb, aluminum honeycomb to soften the blow. And you can see the first time it didn't do a great job of softening the blow. So, that's what a test is for, right? To do all kinds of experiments and to figure things out. But there's a bunch of innovation kind of buried in there. This is a tilt-up umbilical. Some of the other arms in the launch equipment test facility right now are using hinges and hinge boxes from the Apollo program, from the Apollo Access Arm, and some of the other swing arms in the Apollo program. So if you go to the next slide. So another little piece of innovation, it's old hat nowadays, but we used UAS imagery. And we wanted, first of all, this is the video version of flying around the mobile launcher. And first of all, holy crap, that's an amazing picture. But give you an idea for size. Again, size is everything down at the Kennedy Space Center. If you go 3 floors down, you can see some people moving. And give you an idea for the size of the tower. As the UAS is flying down, incredibly steady, by the way, and I'll touch on that in a minute. But you can see the rails on either side. That allows us to move the orbiter access arm and the Orion service module umbilical when EM2 comes. We can just move those depending on where the hatch is located and where the umbilical plates, where the access points are located. So the crew would exit in an emergency egress situation to the right-hand side. There you see the beam that was sticking out the right-hand side. This is UAS is flying around a little bit more. You can see the RPSF in the upper right-hand corner. And also in the upper right-hand corner, you see a mobile launch platform. That was the shuttle version. Notice in this version that there is actually some holes. Some access panels have been removed. That's because we had to beef up the structure and at the same time make it lighter. Now, lighter is relative to you and me. a few pounds is probably maybe not a big deal. With the rocket on it, this is going to range between 19.5 and 20.5 million pounds. So we were actually concerned about the planet Earth supporting this structure. So the crawl away to the right-hand side there is actually getting some assessments done to make sure we can handle the turn between pad A and pad B, and we can head off to pad B and put it up on the stand. You can see in there in the center, we kind of flew by the flame hole. That had to be modified, of course, because Ares 1X was a single stick, and the SLS has got the two solids, and then the core stage in the middle. So all of that is in work. We're in the process now of attaching GSE up and down that tower and arms up and down that tower. So we used the UAS to do two things. One was a video, and one was a scan. Actually did a down to about 1/4 of an inch, maybe less than 1/4 of an inch, scan sensitivity. And what it pointed out to us is that the as-built is not what was in the drawing system in some cases. So one of the things we learned was there was a construction contract to just build the mobile launcher, and then there were separate contracts to build the arms and umbilicals, because we didn't figure that an A&E would be very good at umbilicals. And I think we were right about that. But in the process of putting this tower together, you have to make field changes every now and then. So you have to move a pipe 3 or 4 inches, 6 inches, 10 inches to the left or right. Well, that was supposed to be in a certain position when you installed the umbilicals and the rest of the GSE, and it turns out it's not. So we have used that scan, and we've used that as-built configuration, and we bounce it against our GSE installation requirements, all using this. It's new technology for us kids, but it's what the kids are now using on a regular basis. So we took advantage of that, and we have probably, I would say we have examples at least from 3 generations working on the design and development of this thing. It's really, really exciting to see it come to fruition. Next slide. Wanted to show you inside the VAB on the, let's see, the left. Still the left, yeah. You can see that for a while there we had signs in VAB High Bay 3, and that's where the SLS is going to be stacked. And you can see where the shuttle topped out, and then you can see where the SLS topped out, and where the Saturn V is just slightly above it. We had to do some major mods in there, including removing essentially a 3-story building using the 325-ton crane. On the right-hand side, you can see platforms. We're in the process of building. We've actually inserted 7 of the 10 platforms and 6 of the 10 platforms on one side. Now, each half of a platform, think of these as the world's largest kitchen drawers. They are essentially 270,000 to 360,000 pound kitchen drawers. And they slide in and out of rails, and then they meet in the center and allow you to work around and gain access to the appropriate points. I stress that because size does matter here. And when we first lifted the first platform, this was several months ago now, much to the designer's surprise, and not really to our surprise, when you lifted up 270,000 pounds that was not uniform in shape, by the corners, you're going to get flex. Now, think about 70 feet by over 100 feet by 70 feet, 270,000 pounds with a divot in it. All right? The platform flexed about 3 inches. And we couldn't get it into the rails. So imagine your kitchen drawer, whatever junk drawer you have in the kitchen, right? You have 4,000 pounds of stuff in there. And it bends the drawer, and it makes it hard to slide in. So we used a lot of design viz capability to figure out what we needed to do, and then get these panels and rails installed. In the lower right, down at the bottom of the lower right, you can see the tail service mass. I used to tell people during the shuttle program you had to hit 7 on the elevator button to get to the 0 level of the mobile launcher. Each of those tail service masts is over 30 feet high. We have both of them in the launch equipment test facility right now. Werner von Braun really had 4 big things eating his lunch during the Apollo program. It was systems engineering, it was configuration management, it was combustion stability, POGO mostly, and it was umbilicals. They used to call the launch equipment test facility the arm farm, and I still do. We're using all kinds of new tools and techniques to try to get these arms right, because they all have to work within seconds of each other. They all have to respond to a launch release system command in the millisecond time frame, and it's got to move stuff that's that big. Next slide. So, talk about a little bit of innovation here, and I'm a big fan of stopping and looking around, and I'm a big fan of looking outside your swim lane. If you've been working in a system or a project or a program for such a long period of time, that's your swim lane. You're an expert, absolutely. But there may be stuff going on around you that you're not noticing because you're so busy keeping your head down and coloring. Brown paper bag in the upper left, during the processing of the US lab, they had all the hardware installed. They were just about to button things up, and they found water in the bottom of the bay, in the Eclipse Bay in the US lab. Didn't know where it was coming from. Didn't have an idea where it was coming from, wasn't sure where it was coming from, and didn't have a way to simply leak check it without opening up the bay and starting over. So somebody recommended lay out a brown paper bag and see where the water's dripping. Very simple, very straightforward, probably doesn't meet cleanliness requirements, but it got them in the direction of the water separator, humidity separator. I'm not sure what they call it on station. But it got them in the vicinity of the humidity separator, and they found a leak spot and torqued the fittings and redid the leak check, and everything was good to go on the US lab. And it was just offering up maybe a different way of leak checking. Upper right-hand corner, just a standard ohm meter. During SDS-26R, almost terminal countdown, the crew was getting into the crew module. This was after Challenger, so the crew had new suits. And the suits were purged and pressurized with fans. And several of at least two of the astronauts went into the White Room and their fans quit. Now, it was really, really important that these fans worked because those suits were new, they were airtight-ish, and they had to be able to withstand a certain amount of pressure, and they used the fan to keep them cool because the first crewman in is there for about 2.5 hours, nominal. So it's a long time to be laying in there at a 7-degree angle on your back. The fans quit. So we were thinking about what to do. We scrubbed for the day because the fans didn't work. Somebody came up with the idea that they knew that the mechanisms people, when they closed the hatch for launch, they did a continuity check. So we knew they had an ohm meter in their bag. So we came over the net and asked the technician in the White Room to go downstairs and get the, if he didn't have it with him, get the ohm meter from his hatch continuity check toolkit. And he went up there and he found out that it was just a bad fuse. So they replaced the fuse and off we went with 26R. It was a very successful mission. Lower left, I just wanted to look for a blow dryer, and I can't tell you how hard it was to just pick a damn blow dryer. Now, back then, you would have found four things in a Sears catalog. But currently, there's a gajillion videos, so I tried to find the most space-agey looking blow dryer. The reason I have this on the page is because the halon bottles in the crew module of the space shuttle had a fluid in them, and they were tucked behind all the avionics. Now, we had a requirement to make sure that there was fluid in the bottles. You needed to know that, that your fire suppression system was ready and capable of working. So we struggled with ideas, and somebody came up with the idea of using a hot air blow dryer and an infrared camera. So we used a hot air blow dryer, literally off the shelf hot air blow dryer, and just blew a little bit on the halon bottles in the back behind the avionics bays, and then took a picture with an infrared camera. Of course, back then the infrared camera was like helium-cooled liquid nitrogen something, and it was about this high. But we took pictures, and we were able to verify we actually changed the OMRS-D to say where the shadow line was in the bottle. And that's how we verified quantity. Now, none of that is in the ASME handbook for leak checking, and but it was a simple way, looking outside your typical space, it was a simple way. In the lower right-hand corner, just talk about the last one, I think. That's kind of a picture of the aft section of the orbiter without the engines installed. If you ever had the opportunity, distinct pleasure of going inside the aft of the space shuttle, it was like no other place. There is no way that thing got off the ground on a regular basis. It was just incredible. And we had what we call a flash evaporator system in there, and we circulated recirculated Freon through cooling loops, and we splashed water on it, and the water vented out the sides of the shuttle aft. We had a leak. We were having rust problems, and so we had a leak in those coils. Now, the only way to helium mass spec leak check something that size was to pressurize it. What you would end up doing is filling the aft with helium, and you have no way of separating the leak from the intended purge. So we borrowed an idea from the helium signature test in the main propulsion system leak checking process, and essentially what they did is they stuck the engine in the aft, made sure the aft was secured except for the aft hatches, aft doors, access doors, and they regulated the purge through the aft with a regulated concentration of helium, so they knew ahead of time. Then they pressurized the engine itself, and based on the concentration they got at the aft doors, they could tell if the engine was leaking. So we borrowed that idea from the main engine people and tested an environmental control and life support system coolant system. Next slide. So this, to me, is the ultimate in looking around. It's also the world's creepiest selfie. Literally, how they operate the Mars Curiosity rover is they stop and look around. They have to stop and look around. They see new things. They make adjustments to their schedules. They take different samples and they go in different places. They do that by stopping and looking around, and that's what I would ask you to do here.